Okay, we're back. All right, I believe last time where we left off we were talking about thermochemical equations. And remember, a thermochemical equation is exactly the same as a regular equation. It just has one more piece of information in it. And that one more piece of information is the amount of heat either given off or taken in, or what we call the delta H, which is called the enthalpy, which is the amount of heat given off or taken in at constant pressure. So it is a Q, really. It's just a special type of Q. It's Q at constant pressure. But the amount of heat given off, taken in, you can think of them both as in terms of that. Okay? Now, do you remember in chapter 4 we did that stoichiometry? And remember I said that was really important because if you couldn't do that, then you probably were not going to make it very far in this class. Well, it turns out that many of these chapters have their own little version of stoichiometry. And chapter 5 is no exception. So what we'll talk about today is let's talk about the 3 rules of thermochemistry here. Again, these are not the 3 rules of thermochemistry, but they are the 3 rules of chemistry I have decided to talk about. All right. So let's start with the first one. The first rule is delta H is directly proportional to the amounts of reactants and products. Okay. Put simply, 1 stick of dynamite, big boom. 2 sticks of dynamite, bigger boom. Actually, exactly twice the boom. You know, if I had a half stick of dynamite, then you would only have half the boom. You know, the amount of heat given off or taken in is directly proportional to amounts of reactants and products. So how do I use this particular rule? Well, say for example, H2O solid goes to H2O liquid. This is just a fancy way of saying what? Yeah, you're just melting ice. What you're doing, you're going from the solid to the liquid. To melt ice, do you have to add heat or do you have to take away heat? You have to add heat, right? Well, how much heat do you have to add? Well, delta H for this reaction is positive 6.00 kilojoules. So here's my thermochemical equation. Okay, is this endothermic or exothermic? It's endothermic. How do I know this? Positive delta H. Does that mean this reaction takes in heat or gives off heat? Well, it takes in heat. Positive 6 kilojoules. This is something actually called the heat of fusion. The heat of fusion, which we'll talk about in a later chapter, is the amount of heat it takes to go from the solid phase to the liquid phase. Or, conversely, it's actually the amount of heat you have to take away from the liquid phase to go to the solid phase. It's just going kind of backwards there, which we'll talk about in a minute. But yeah, that's called the heat of fusion for water here, for ice. Okay? Given that equation, what is the delta H when 1 gram of ice melts? Okay, well, what do we know? Well, we know we've got this equation, and we also know we've got 1 gram of ice, right? So we're going to start out, we're going to write down 1 gram of ice, or water here in this case. All right, draw a time sign. Okay, where am I trying to get to? Well, I'm trying to get to delta H here. Of course, that's in kilojoules, right? Normally when we express delta H's, we express them in kilojoules. So I'm trying to get to kilojoules. Okay. Do I know a direct relationship between grams of ice and kilojoules of energy? No, I don't. Do I know a relationship between kilojoules of energy and anything? Well, actually I do. That's in my thermochemical equation. Notice for every 1 mole of ice that I melt, how many kilojoules of heat does it take? I have to add 6 kilojoules. So see, what I can do is I can actually use this as a factor. You know, remember when we went from mole to mole, we used coefficients of the balanced equation? Well, just think of this as another coefficient. It's pretty much the same thing. When I take 1 mole of ice and change it into 1 mole of water, I have to add 6 kilojoules of heat. Every time I add 6 kilojoules of heat, I can melt 1 mole of ice, and I can form 1 mole of water. So just think of it as another coefficient in your balanced equation, because that's really kind of all it really is. Your thermochemical equation gives you the relationship between moles of stuff and kilojoules of energy, kilojoules of heat given off or taken in. So, according to my little equation here, for every 1 mole of ice that I can melt, it's going to take 6 kilojoules of energy. All right? So if I can somehow get to moles here, I can get to kilojoules, but I'm in grams. So how do I get from grams of ice to moles of ice? What do I use? Well, I use the molar mass, use the formula mass, chapter 4. See, if you don't know how to do that, you're just dead in the water here. You know, if you don't learn how to do that stuff, it's gonna come back to haunt you time and time and time again. So learn it. So how do I figure out how much 1 mole of ice, which is H2O, solid, weighs? What would I do? Well, I'd take the mass of an oxygen, and I'd take the mass of 2 hydrogens, I'd add them together. So this is 16.00, this is about 1.008 times 2, 2.016 plus 16.00, so around 2 places past the decimal, 18.02. You can check my math if you want to. What goes on top, what goes on bottom? We want to put the grams on the bottom so they'll cancel. You want the moles of water up here on top. So if I quit right here, didn't do anything else, I'd be in moles of ice, water. All right, but we want delta H. We want to be in kilojoules. So now I go up to my thermochemical equation, say, okay, for every 1 mole of ice, I have to add 6 kilojoules. And what I'm going to do is I'm going to use that as a factor. So I'm going to put 1 mole of ice on top over 6 kilojoules on the bottom, or 6 kilojoules on top over 1 mole of ice on the bottom. Which way do I want to draw my factor? Well, I want the moles of water on the bottom. Why? Well, because I want those to cancel out, see? So 1 mole of ice, positive 6 kilojoules. That cancels that. The only thing I have left here is kilojoules, which is what I'm looking for. That's my delta H. So now I do the math. So 1 times 6, which is 6, divided by 18.02, run it through the calculator. I believe you'll find that to be 0.333 kilojoules, positive. Notice that if I have to add heat to melt a mole of ice, I still have to add heat to melt a gram of ice. But notice if I only have 1/18 of a mole of ice, it takes 1/18 as much heat. Delta H is directly proportional to the amounts of reactants and products. And so what we do is we use these relationships here in our thermochemical equation to do some stoichiometry stuff here. All right, so let's try another one. So see if you can do this one. So here's a thermochemical equation. H2 plus Cl2 goes to 2HCl. This is hydrogen chloride. If I had hydrogen chloride dissolved in water, what would it be? Well, that'd be hydrochloric acid, right? But hydrogen chloride as a gas by itself is just hydrogen chloride. All right. Delta H for this reaction is negative 185 kilojoules. Is that endothermic or exothermic? Exothermic. Does it give off heat or take in heat? Gives off heat, negative delta H. Okay. So what do I know in this particular problem? Well, I know that 74.8 kilojoules of heat are given off. So that's what I'm going to write down. I have no idea where 72.3 came from. Just maybe I had that in my head. I don't know. But it should be 74.8. See, if you want to change it, you can. But that's what it should be. All right. Kilojoules. We're going to draw a factor. Okay. So do I know a direct relationship between kilojoules of heat given off and grams of HCl that are formed? No, I don't know that. Okay. Do I know a relationship between kilojoules of heat given off and anything? Well, I do, because I've got my little balanced thermochemical equation up here, see? So I know that every time I form 2 moles of HCl, 185 kilojoules of heat's given off. See, your balanced thermochemical equation gives you the relationship between the heat given off and taken in and the number of moles here. Again, treat it like it's just another coefficient in your balanced equation. That's what I would do. All right? So what goes on top, what goes on bottom? Well, you want the kilojoules on the bottom, so they'll cancel these up here. So for every 2 moles of HCl, 185 kilojoules of heat's given off. So I cancel out the kilojoules there. And that gives me moles of HCl. But the problem's asking for what? Grams of HCl. So how do I go from moles of HCl to grams of HCl? I use the formula mass. All right, so I look up a hydrogen, which is about 1.008, my periodic table, and I look up a chlorine, which is about 35.45, And so I get 1 mole of HCl is 36.46 grams of HCl. At least I got that part right. All right, so what goes on top, what goes on bottom? Well, you want the moles on the bottom, so they cancel here, and you want to be left with grams, which is what you're looking for, and so you're done drawing factors. So now we do the math. So negative 72.3 times 2 times 36.46, divide that by negative 185, and you end up with positive 28.5 grams of HCl. And there's your answer. If you end up with a negative here, what you probably did is you probably messed up on your sign convention here, but the number will probably be right. So, check that. If you get a negative grams, obviously you can't get a negative gram. Just double check your signs there, but the number's probably okay. You just either forgot to put a negative in here or here or whatever. But yep, 28.5 grams of HCl. That's the answer. So see, it's stoichiometry. It's the same stuff you did back in chapter 4. It's just one extra thing, and that's kilojoules. But it's really the same thing. It's not something totally new. You can do this. What I would do here is I would be careful. Sometimes what books like to do is they'll throw a calorimetry problem at you, like this, and then they'll throw a stoichiometry problem on top of it. And so they'll say, suppose combustion 1.6 grams of the bomb calorimeter, blah, 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 blah. What's Q for the reaction? And then they'll say, what is Q for 1 mole of methane? And so the way you do a problem like that is you go ahead and do the calorimetry problem, and then you use that as a factor. You say, okay, well, I know for every 1.6 grams of methane I burn, 89.4 kilojoules of heat is given off. Use that as a factor to determine how much 1 mole. So start with 1 mole, go to grams, and then use this many grams gives me this much heat to get to kilojoules. And that gives you kilojoules per mole. Rewind that if you didn't catch all that. But it's, yeah, sometimes they like to do that. They'll put a calorimetry problem and a stoichiometry problem in the same problem. See if you can do them both. All right? Okay. So that's rule number 1. And it's just, again, it's just stoichiometry with one extra thing. All right? So quick recap here. If I need to go from grams to moles or moles to grams, what do I use? I use my formula mass. Okay, chapter 3. If I need to go from atoms of something to moles of something, what do I use? I use Avogadro's number, chapter 3. If I need to go from moles of something to moles of something else, what do I use? I use my coefficients in my balanced equation, that's chapter 4. And if I need to go from moles of something to kilojoules of heat or kilojoules of heat to moles of something, what do I use? I use my coefficients in my balanced thermochemical equation. All right, so see, again, it's the same stuff you already know how to do. It's just one more thing on top of it. You can do this. All right, second rule we need to talk about. Okay, and this one's a little bit easier. All right, delta H for a reaction is equal in magnitude but opposite in sign to delta H for the reverse reaction. All right, so for example, if I take H2O solid to H2O liquids, we're melting ice here again, I have to add 6 kilojoules of heat to get that to happen, right? What if I don't want to melt ice? What if I want to go the other way? What if I want to make ice? How much heat do you think it would take to go from liquid water, 1 mole of liquid water, to 1 mole of ice? Well, if I have to add 6 kilojoules of heat to get the ice to melt, I have to take away 6 kilojoules of heat to get it to freeze. Delta H is equal in magnitude, but opposite in sign to delta H for the reverse reaction. So, if you take a chemical equation and you flip it, then the amount of delta H is still the same, but it changes sign. It goes from positive to negative, negative to positive. And that's rule number 2. Okay, and that wasn't too bad. That's pretty simple. Well, we're going to make it up with the third one. The third one is called Hess's Law. And this is probably the hardest thing, I think, in the whole chapter. If you can do Hess's Law, then you can do probably about anything in chapter 5. All right. Hess's Law goes a little something like this. If equation 1 plus equation 2 equals equation 3, then delta H1 plus delta H2 equals delta H3. All right. Put simply, if you can take two equations and you can add them together, then you can simply take the delta H's for those two equations, add them together, and that gives you the total delta H for the third equation. All right. This is usually used to calculate delta H indirectly. Maybe you can't calculate it directly. Maybe it's a multi-step process. It just doesn't happen in one step. Maybe you're dealing, like for example, this next problem with something that's poisonous. Maybe you really don't want to try to measure this directly because it's kind of dangerous. Sometimes what you can do is you can kind of indirectly calculate it. All right. So let's see what we can do. So here's a couple of problems for you. Okay, so the first one, we'll start out relatively easy here. Calculate delta H for this equation. We've got carbon plus a half a mole of oxygen goes to CO. What's CO? That's carbon monoxide. Is this something you want to be messing with? No, it's poisonous, right? So this is certainly not something you want to be generating in the lab, outside the fume hood. The other problem with it is normally when you take carbon, you combine it with oxygen. Do you normally get large amounts of carbon monoxide? Well, no, generally you get large amounts of carbon dioxide, which is a good thing. All right, so experimentally this might even be kind of hard to measure. All right, so is there any way I can calculate it? Well, let's say I look up for equations for it in the appendices back here, and I don't find anything that's exactly what I want. But what I do find is I find these two equations. I've got CO plus a half a mole of O2 goes to CO2, and delta H for that is negative 283.0 kilojoules. And I find carbon plus a full mole of O2 goes to CO2, and delta H is negative 393.5 kilojoules for that. All right. Given these two equations right here, is there any way I can use these two equations to calculate delta H for this equation? Well, probably so, or I wouldn't have put it as a problem, right? Okay, so how are we going to do this? Well, what makes Hess's law kind of difficult, when students try to do Hess's law problems, they take what I like to call the jigsaw puzzle approach. In other words, they take their equations and they start adding them together and flipping them over and multiplying by 2 and just trying to get them to fit. So it's like taking a jigsaw puzzle and just randomly trying pieces, and trying to fit it together and get the complete puzzle. If it's a very small puzzle, you can probably get away with that. But if it's one of those, 1,000-piece puzzles where, like, every piece is blue. Somebody sent me a periodic table puzzle one time. It had pictures of all the elements in the periodic table, which you would think would be pretty easy to put together. But every single one of those pieces was like black and gray. Every single one. It took me like days and days to do that thing. And I'm one of those people, if I start something, I just got to finish it somehow. And I hate they did that to me. But yeah, it's sitting upstairs somewhere. But it probably just putting things together at random is not a really good way to do a jigsaw puzzle like that. It'll take you forever. You got to have a strategy. Maybe you find all the blue pieces, and find all the corner pieces, and the edge pieces and things like that. Well, it's kind of the same way, I think, when you do Hess's law. You got to have a strategy. So here's what my strategy is for doing Hess's law problems. Instead of just randomly flipping things and trying to get them to fit together, you're going to say, okay, what am I looking for? Because if you don't know what you're looking for, you're probably never going to get there. So here's the equation I'm interested in right here. Okay? So then what I'm going to do is I'm going to look at the first substance here in this particular equation. So I got C, carbon. All right, then I'm going to ask myself, okay, in the equations that are given to me, is there one and only one equation that contains carbon? Yes, it's this second one right down here. All right, so this is the equation I'm going to use first. Okay, second thing I'm going to do is I'm going to ask myself, okay, what side do I want the carbon on in my final answer? Well, I want it on the left-hand side. What side is the carbon on in the equation that I'm given? What's on the left-hand side? That's a good thing. So we're not going to mess with it. All right. Third thing I ask myself is, okay, how many moles of carbon do I really need here? Well, I need 1 mole. How many moles of carbon do I have here? Well, I have 1 mole. So I have the carbon on the right side, proper side, and I also have the proper amount. So what we're going to do is we're just going to use that equation as is. So I'm going to write down carbon plus O2 goes to CO2. And I know delta H for that is negative 393.5 kilojoules. All right? Okay, now I'm going to go to the second substance here in my equation. And in this case, that would be O2. Do I see O2 in one and only one equation? Well, no. It's actually in both equations. So how do I deal with that? Well, the short answer is I don't. I skip it. I move on to something else. All right. What will happen, generally speaking, is one of two things. Either the problem will just magically go away when you're done. It'll fix itself. Sometimes if you just ignore problems, they fix themselves. It doesn't usually work that way, but sometimes it does, I guess. The other thing that could happen is you'll end up at the very end with only one equation you haven't used. You'll use that equation to fix that one. And those are probably the two things that usually will happen to you. Does that happen to you in real life? Probably not. Does it happen to you in the book? Yeah, usually does. So if you see something in more than one equation, just skip it. Don't worry about it. Okay? All right, so what do we got next? Well, we got CO. Do you see one and only one equation that contains CO? Well, yeah, this top one does here. Okay. What side do I need the CO on? Well, I need it on the right-hand side. What side is it on down here? What's on the left-hand side? How can I fix that? Well, what I can do is I can take this equation and I can flip it. I can turn it around. All right? How many moles of CO do I need? I need 1. How many moles of CO do I have? I have 1. All right, so I've got the right amount. It's just on the wrong side. So what we're going to do is we're going to take this entire equation here and we're going to flip it. Okay, so when we flip this equation, this becomes CO2 goes to CO plus a half a mole of O2. Okay, now delta H for this equation, is it negative 283.0? Well, no, because it's not the same equation. But remember rule number 2? When I take an equation and I flip it, delta H is equal in magnitude, but what? Opposite in sign for the reverse reaction. So when I flip this equation, delta H for this is not negative 283 anymore. It's the negative of negative 283, or it becomes positive 283.0 kilojoules. All right. Notice we used each of those equations once. Is that the way it works in real life? No. Is that the way it works in the book? Pretty much always works that way in the book. You know, you'll probably end up using every one of them they give you at least once, or once. Okay? So, now, if I can take these two equations and I can add them together and get this equation here, I can simply add these delta H's together. That's Hess's law. All right? Well, how do you add an equation? I can add numbers, but how do you add an equation? Well, it's pretty simple. What you're going to do is you're going to write down everything on the left-hand side of both equations, and you're going to draw an arrow, and then you're going to write down everything on the right-hand side. That's how you add an equation. Before you do that, though, sometimes you can simplify things. If you see two things on opposite sides of the equation, you can cancel those. If you see the same two things on the same side of the equation, you can add those together. So let's see what we've got here. Do you see anything here that is the same? Well, here's a mole of CO2 over here on the right. Here's a mole of CO2 over here on the left, so I can cancel those out. Here's a mole of O2 on the left in this equation, and a half a mole of O2 in this equation over here on the right. So what we're going to do is we're going to get rid of this half a mole of O2 here. We're going to get rid of a half a mole of this. So if I get rid of a half a mole, and I had a full mole to begin with, how much do I have left? Well, I have a half a mole of O2. Do you see anything else that's the same? No, everything else is different. Okay? So now all we got to do is just write down everything that's left over on the left-hand side of both equations. So that would be a carbon. That would be a half a mole of O2. All right? And then write down everything that's left over here on the right-hand side. That would be a CO. Is this the equation we were looking for? Yeah, sure is. So if I can take these two equations, add them together to get my third equation, I can take these two delta H's and add them together, and I can get the delta H for the third equation. So negative 393.5 plus 283.0. Don't forget the negative signs. Minus signs are really important in this chapter. Don't leave those out. Add those together, you get negative 110.5 kilojoules, and that's your answer. And that's Hess's law. So instead of just trying to randomly turn things around, go in with a strategy. It keeps you focused, and hopefully you can get to the correct answer that way. All right. Well, that one you might have been able to do in your head. I guess if you sit there and kind of flip things around, it wasn't too bad. But what if they get a little bit more complicated? How bad could this get anyway? Well, I'll tell you this. See this problem right here? It won't get any worse than that. All right, 3. I'll promise you I won't put anything more than 3 on the test. When you take an ACS exam, which you will, maybe next semester, the ACS exam, is this going to be on there? Yeah, it's going to be on there. They always throw a Hess's Law problem on there, I'm just telling you. Is it going to be 2 or is it going to be 3? Don't know. It depends on what kind of mood they're in. Sometimes they'll give you 2, sometimes they'll give you 3. Sometimes if they're in a really bad mood, they'll put 1 with 2 and 1 with 3. But I don't think I've ever seen one with more than 3. So this is probably as complicated as it gets in Chapter 5. If you can do this, I think you've really got a fighting chance here of getting through this chapter somehow. All right, so let's give it a shot. Given the following thermochemical equations, there we go, a little easier. Okay, so boy, I got 3 of them here. So 2H2 plus O2 goes to 2H2O, delta H negative 571.6. N2O5, this is dinitrogen pentoxide, plus H2O. Water goes to 2HNO3, that's nitric acid there. And delta H for that's negative 73.7. And a half a mole of N2 plus 3/2 moles, 1.5 mole, of O2 plus a half a mole of H2 goes to HNO3, and delta H for that is negative 174.1 kilojoules. Okay, so given that information, calculate delta H for the formation of 1 mole of dinitrogen pentoxide from its elements in their stable states at 25 degrees Celsius and 1 atmosphere. Okay, well, first thing you got to do in this problem is you got to have something to work toward. If you don't have an equation to work toward, you won't know where you're going. All right, so what that means is, in this case, they didn't give you the equation you were looking for. You have to come up with the equation on your own. But it's not too bad. What are we doing here? We're forming 1 mole of dinitrogen pentoxide, right, from its elements in their stable states. Okay, so we're forming 1 mole of what is dinitrogen pentoxide? Well, if you remember naming compounds, 2 of these, 5 of these, so N2O5. Okay, what are the elements in their stable states from that we form dinitrogen pentoxide from? Well, I know that nitrogen is found as N2 in the atmosphere, and I know that oxygen is found as O2. All right, and so now we've got to balance the equation. Now, there's a couple of ways you could go at this. If you wanted to, you could balance this equation, and you'd end up with a 1 here, a 5 here, and a 2 here. And if you did that, you could go ahead and calculate delta H. But when you calculate delta H, you're actually calculating the amount of heat it takes to form 2 moles of dinitrogen pentoxide, not just 1. So how could I get to the correct answer? Well, you can just take the answer you got and simply divide it by 2. See, it takes this much heat to form 2 moles. Well, I guess it takes half as much heat to form 1 mole. And you could do it that way. Or the other way you could do it is you could just lock this in as a 1. We're going to fix this as a 1. Okay, and then we're going to make fractional coefficients over here to make that fit. If we lock this in as a 1, then we can just calculate delta H, and whatever that is, that happens to be the true answer. All right, so let's try that. Let's lock this in as a 1. Okay, so how many nitrogens do I need on the left-hand side? Well, I need 2. Do I have 2? I do, so that's good. How many oxygens do I need? Well, I need 5. But this is O2. I can only add them 2 at a time. All right. Do you see that if I had 2 moles of O2, that's 4 oxygens? If I had 3 moles of O2, that's 6 oxygens. So what I need is I need 2.5 moles of O2 to give me my 5 oxygens. 2.5 moles in fractional form is 5 over 2, or 5 halves. So that's where we got the 5 halves from. And now my equation is balanced. And since I've locked this in as a 1, I can just go ahead and calculate delta H, and it will actually give me the correct answer. Make sense? Okay, so now we have our equation that we're actually trying to get to. We're getting somewhere here. So now we got to figure out how to get there. So what's the first thing we do? Well, we look at our equation. So what have I got here? I've got N2. All right, do you see N2 in one and only one of these equations? It's actually in the third one, and only in the third. What side do I want it on? I want it on the left-hand side. What side is it on here? Well, it's on the left-hand side, so that's a good thing. Okay, how many moles do I need? I need 1. How many moles do I have? I only have a half. So how am I going to fix that? Well, I'm going to multiply this entire equation by 2. And that would give me 1 mole of N2. I have to do the whole thing. Can't just do the nitrogen. All right. When I multiply this equation by 2, what does that do to this delta H? Well, this delta H is twice as much because first rule, delta H is directly proportional to the amounts of reactions and products. So it's on the right side, proper side, which is good, but I need to multiply this by 2, so that's what we did here. So multiplying this by 2 becomes N2 plus 3O2 plus H2 goes to 2HNO3. When I did that, I take this delta H and I have to multiply it by 2 since I multiplied the equation. So delta H for this reaction is negative 348.2, which is 2 times 174.1. See, you got to get it on the proper side, got to get the right amount. Okay, what else we got here? Well, we got O2. Do you see O2 in one and only one of these equations? Well, no, it's here. It's also here. So what are we going to do about that? We're going to skip it. We're going to move on. All right, so what else do we have? Well, we got N2O5. Do you see N2O5 in one and only one of these equations? What's in this second one here? All right, what side do I need the N2O5 on? I need on the right-hand side. How much do I need? I need 1 mole. What side is it on up here in this second equation? What's on the left-hand side? How can I fix that? Flip the equation. All right, how much N2O5 do I have here? Well, I've got 1 mole. I needed 1 mole, so I don't have to multiply by anything. I just have to flip the equation. So that's what we did here. We simply took this equation. So now it's 2HNO3 goes to N2O5 plus H2O. All right, if delta H for this was negative 73.7 kilojoules, what's delta H for this one right here? Well, positive 73.7 kilojoules. We flipped the equation, and so therefore we changed the sign. All right. Well, do you remember that oxygen that was in more than one equation? Well, now we got to fix that. We can check and see if we can add these two together and see if we get the right number of oxygens. We got 3 O2s over here. We have no O2s over here, so that's not 5 halves. So we have, sometimes if you're lucky, your oxygens in this case will just magically come out. We're not so lucky this time. So how do we fix this? Well, notice there's one equation we haven't used yet, and that's this top equation up here. Is O2 in that equation? Well, look at that, sure is. All right, and so yeah, usually most of these Hess's law problems, that's what'll happen. So either whatever's in more than one will just magically fix itself, or you can use whatever's left over to fix it at the end. Okay? So notice I have 3 O2s over here and nothing over here. And I need what, 2.5 when it's all said and done? Do you see that if I can somehow get a half a mole of oxygen on the right-hand side, what I can do is I can cancel out that half a mole of oxygen, cancel out a half a mole of oxygen over here on the left-hand side, And instead of being left with 3, now I'm left with 2.5, which is 5/2. Same thing, just in fractional form. So essentially what it comes down to is I got to figure out a way to get a 1/2 mole of O2 on the right-hand side. Okay, well, in this equation, is it on the right-hand side? No, it's on the left-hand side. How can I fix that? Flip the equation. When I flip the equation, what's that do to the sign? Change the sign. Do I have the right amount here? No, I don't have the right amount. I need a 1/2 mole over here. I've got a full mole here. So how can I fix that? Well, I can also divide this entire equation by 2, or multiply it by 1/2, whichever way you prefer to think of it, same thing. All right, so to get this equation the way I want it, I need to flip it and divide by 2, or multiply by 1/2. Okay, so here is the equation as I need it. We flipped it, and we also divided it by 2, so I got H2O goes to H2 plus a 1/2 mole of O2. Delta H for this equation is change the sign and multiply by 1/2. So if you have to divide by 2, the equation by 2, you divide the delta H by 2. If you have to multiply the equation by 3, then you'll multiply the delta H by 3. See? So divide by 2, multiply by 1/2. So negative 1/2 times negative 571.6. So change the sign, divide by 2, positive 285.8. All right? Okay, well, Hess's law says that if I can take equation 1 plus equation 2 plus equation 3 and add them together to get equation 4, then delta H1 plus delta H2 plus delta H3 equals delta H4. So we start canceling here. So do you see anything that's the same on both sides? Well, here is an H2 on the left-hand side of this equation. Here's an H2 on the right-hand side of this one. Those cancel. Here's two HNO3s here. Here's two HNO3s here. Those cancel. Here's an H2O here. Here's an H2O here. Those cancel. Here's a 1/2 mole of oxygen over here. We did have 3 over here, so we're going to get rid of 1/2 of that. So we're left with 2.5, or 5/2. And then we cancel this out, and we're left with 5/2 O2 here. Is there anything else that's the same? No, I think we're good. So we're going to write down everything left over on everything over here on the left, draw the arrow, and then write down everything that's left over here on the right. So N2 plus 5/2 O2, that's everything that's on the left-hand side, my 3 equations, goes to N2O5 is the only thing on the right. Is this the equation we're looking for? Yes, it is. It is the equation we're looking for. So if I can add these 3 equations together to get this equation, I can add these 3 delta H's together to get this delta H. So negative 348.2 plus 73.7 plus 285.8. Again, pluses and minuses, really important in this chapter. Be very careful. Add those 3 together and you end up with positive 11.3 kilojoules, and that's delta H for this reaction. Endothermic or exothermic? Endothermic, does it give off heat or take in heat? Takes in heat. How do we know this? Positive delta H. That's what makes it endothermic and also makes it take in heat. And that's how you do it. And that's pretty much the hardest problem in the whole chapter. If you can do that, you can do anything in chapter 5. But the key is have a strategy. Know where you're going. Have a strategy to get there. If you start taking these 3 equations here and start flip-flopping them all over the place and dividing by 3 and this, no, just it's too complicated. You won't get it. All right. But if you figure out what you need, sometimes it's given to you, sometimes it's not. Sometimes you got to come up with it and balance it. But no one's going to ask you to come up with the hardest equation in the book to balance. It'll probably be something really, really simple to write, really, really simple to balance, if you're asked. And then just go through each particular substance. Start here, go here, go here. Fix the ones that are one and only one. And then whatever's left over is usually taken care of by the one that hasn't been used yet. All right, and yeah, pretty much in the book, that's the way pretty much all those problems work. Is yeah, you'll end up using every equation once. Usually they won't throw an extra one at you, or you won't have to use one twice or something like that. And usually it's either 2 or it's 3. 3 is about as complicated as you're probably going to end up seeing on a test. If you can do these, you're great. All right, and it's a way to kind of indirectly calculate delta H if you don't have it in the back of your book. You know, the alternative is to go into the laboratory and do it yourself. And chemists are basically lazy by nature. You know, why would we want to go into the laboratory and do an experiment when we could just calculate it on a piece of paper? That saves us a whole lot of time and a whole lot of work, right? We don't have graduate students to do it for us. Why does it work? Side note here. Why does it work? Well, it works because delta H is a state function. What is a state function or a state property? It's a property that is path independent. It doesn't matter how you get there. All that matters is where you start and where you finish. Look, what this is saying is, if I want to take carbon and oxygen and make CO, it doesn't matter if I go there directly or if I take carbon and oxygen and make CO2 and then take my CO2 and break it down to make the carbon monoxide. It doesn't matter if I do it in 1 step or if I do it in 2 steps, I still get the same delta H. It's path independent. If I want to make N2O5 from nitrogen and oxygen, I could do it directly, or I could take nitrogen, add oxygen and hydrogen to it, make HNO3, take the HNO3, break that down to N2O5 in water, and then take the water and break it down into hydrogen and oxygen. It doesn't matter if I do it in 3 steps or if I do it in 1 step, you still get the same delta H. And that's the reason why Hess's law works. It's a state property. Path independent. Well, that was fun, wasn't it? We would love to do like 40 Hess's law problems on the test, correct? Is this something you want to do? Well, probably not. You know, it's kind of complicated. And, you know, it's bad enough when they give you the equations that you use. In the real world, do they give you a problem and then give you the equations that you're going to use to solve it? No. You have to look all those up yourself and find them. You got to know if this is relevant, that's relevant, then you got to go through all of them. It's doable, but it's cumbersome. Wouldn't it be nice if there was an easier way to calculate delta H where I didn't have to use Hess's law? Boy, that would be nice, wouldn't it? Well, maybe that's what we'll talk about in the next video. We'll talk about a couple of other ways to calculate delta H that don't involve Hess's law. So yeah, you might want to show up for that one. But we're running up on almost 50 minutes now on this one. It's a little longer video. So I guess it's probably a pretty good place to stop. So we'll quit from there on that note, and I guess we'll see you next time. So